Okay, sorry about that. Pending that function. So as I said before, log_n usually happens with base 2 in terms of binary search. So if you were looking through 64 gigabytes, right, we saw that actually taking this log base 2 is actually going to be just 36 comparisons for this huge amount of data. Whereas if you did a linear search, this is going to actually be, well, basically n, right? 64 times 10 to the 9th comparisons versus 36. So binary search is extremely dramatic in how much of a speed gain you get when you get to use it. It also basically operates on just pointers by moving a left boundary and a right boundary over a set of data. And all you do is you just update one of these each time. And basically as the bounds narrow, the problem narrows. And we'll see a bit more about that later today. So it's also used to search through sorted offline data. You can imagine some use cases where you care about things like order history, which is naturally ordered by dates. You can think about phone number lookups because phones numbers have an ordering, right? So 510, phone numbers that start from 510 can be clustered together, and you can tell that you're going to find all the numbers within 510 before you find all the numbers that start with 513, for example. So this is offline sorted data. There are ways to search through online sorted data where data comes in as a stream. Binary search is not really suited well for that because it operates on data that's already static and usually over an array. And if you were to insert something into an array, that cost is usually O of n in the general case. So just keep in mind that the problems that we'll be talking about today generally have to deal with when the data is sorted offline, meaning that it is already done and you're not accepting new incoming data. It's possible. Okay. Are you seeing it update now or no? Okay. No worries. Yeah, try that. Hey there. Okay, cool. No worries. I really appreciate you letting me know. It could have definitely been another problem on my end. All right, so yeah, it is also possible. There are some designs I've seen for nearby location services, and these are used in things like when you have a map of the world and you break things down, into different, into a type of system where you kind of think about things as a quad tree. Okay, I ordered these numbers completely wrong. But if you think about breaking up a world map into a different space, you can kind of think about segmenting it further and further. And the way that you segment further and further is to add more ones or zeros depending on which quadrant you are in of a current tile. It's actually possible to use binary search to kind of help with doing some of that. I'm not a complete expert on this, but I've seen some designs for a Yelp-like thing where you need to find nearby businesses, where if you simply divide up the world into these things called geohashes, because they are well ordered and sorted, you're able to actually use binary search for some of the problem. So those are some interesting applications of binary search. I don't have a super concrete example of that, but I can probably provide a link at some point. I'm not sure if it's used in real world. But those are some interesting ways to think about using binary search. It's not just through integers, it's not just through strings, right? You really come up with formulations, and when you have data sorted that's totally ordered, binary search might be a fit. So just keep that in mind. Right. So another application of this is git bisect. And basically, say you have like version 4.0, right? But then you have an incoming issue, right? And there exists an actual bug. But where is the bug, right? Well, it just so happens that you might have a sequence of other commits, right? And since version 3.0, there might have been a lot of changes that have come through, right? Maybe even 1,000 changes. And just imagine as a developer going through all those different changes, like 1,000 different changes, and seeing where that bug occurred. That's extremely painful, right? So what git bisect allows you to do, it's actually a tool, and it's got documentation. This is actually included with Git itself. You can actually binary search through different revisions, and it will do the binary search for you and just check out commits. And then you can just test the code, run your tests, whether it's manual or whether you created something a little bit more automated, whether that commit showed the error or not. And based off of that, you can start to see and narrow down which change was good and which change was bad. So this is another application of binary search. Again, it's not just for numbers, right? Anytime you have data that's already sorted in an offline manner, binary search is a possible candidate. All right, let me figure out which button clears the screen. Okay, cool. There's also spell checking libraries that kind of use it for some things. You might have used Hunspell without knowing it. It spell checks in both Firefox and Chrome. It's a free and open source project, and they're also on GitHub as well. Why do they use binary search for these specific things? I can't quite tell you, but there are applications out there. The most obvious application is really when you have a sequence of words like A something, B something, C something, right, all the way to Z something. And let's say imagine you typed in a word. I don't know what a word is, maybe corp, right? Wait, no, that's actually a real word. Corf. That's probably not a real word, right? And the spell checker needs to find out, like, well, I want to recommend a word that maybe is a nearby word. One strategy in order to do that, because you have this entire dictionary, is actually, well, there's a nearby word, core, and there's a nearby word, I don't know, this is a bit morbid, corpse, right? And when you binary search, because you actually grab a left boundary and a right boundary, you can actually suggest a window, right, into the dictionary about possible word suggestions. I think Hunspell actually operates on a tree data structure called a trie for a lot of what it does, but this is just like a basic hypothesis for maybe how it uses some things in binary search for what it does. So those are just some use cases that you can keep in mind and hopefully see some of its power. We won't touch on this in today's lecture, but it is actually pretty important in some types of optimization problems. It also is much simpler to code once you get the hang of binary search, and it allows you to avoid dynamic programming techniques, which can be a lot slower. This also works for some types of problems where you might use a heap instead, but this is really for part 2 of this lecture, which won't appear for some time. And it's one of the things that really made me go, wow, binary search is so applicable. All right, so with all that being said, what actually is it, right? Let's talk about how useful it can be. But first of all, got to show you what actually happens. Okay, so here we are. We have 7, right? Let's say we want to find, is 7 in this array? That's really the question that this diagram is asking. So what happens first is that we have a left pointer, right? Oh, the color is not working. Is this color working? Is this color working? This color is also not working. All right, sorry, we only have one color today. All right, so currently we have a left pointer, right? And we also, on the right bounds, have a right pointer. And this sets up the bounds of where we can search in our binary search. You might have seen this from discrete math class. Hopefully this is going to jog a lot of memories for you. So we have this 7, it comes in. What happens, we calculate the middle index. So this is 16 and this is 0. So 0 plus 16, and then we divide by 2. We're at index 8. That's right here. I wish the contrast was a little better for you to see. So this value is 14, right? We compare 7 to 14, and the choice we make now depends on whether 7 is greater than, equal to, or less than 14. Well, we know 7 is less than 14, so what choice should we make about where to search next? Well, we know right now that 14, this is sorted data, so anything to the right of this should not be searched, right? If you're going to look for 7 against 15, 16, 17, 18, or anything else above, we know that that cannot happen. So the answer must lie in this section of the problem now, right? So now, what happens, because 7 is less than 14th, so right actually moves to this spot over here. Depending on how you write binary search, I technically move it to one spot below. So this is actually going to be the middle, minus 1, okay? So now we have our left again, right? And we still have our right. And we did the same thing. So basically we have 0, right, plus 7, okay? And we're going to do integer division. So this would normally be 3.5 if we were doing continuous mathematics, but instead this is going to be 3 because we're going to do integer division. We have to pick one of the middle numbers, right? We can't pick both. So the value for the index is going to be 3. That's this 3 right here. With this 3, we grab the value. That value is 6. We do the same comparison. How does 6 relate to the value we're finding, 7? Well, 7 is greater than 6. So actually, all the values between here to here, right? Actually, we won't find it here, and we know that because the data is sorted. That is an invariant in the problem. Every time we cut out a section, that's the section we're marking that the answer won't be there. We're going to go to the next section. So left is actually going to move to right here. And with our right at 7 and at index 7 and our left index at 4, we're going to do the same thing. We're going to find the average of those two indices again. We're going to look up the value. That value is 8. The value of 8 is going to be compared to 7. We're going to see that the values cannot live here, right? So we move our right bound right here. And then finally, we take the average of these two indices. It's right here again. So that value is 7. When I write binary search, I allow the left to actually equal the right, and that's fine with me. I keep doing the iteration even when the left equals the right. And I do the same comparison. Does 7 equal 7? And it does. Okay, so that's the answer. So just to visualize a bit how many comparisons we did. This was one comparison. This was the second comparison. This was the third comparison. This was the fourth comparison, right? So if you were to linear search through 7, right? Linear search would have in worst case taken 16 comparisons. Whereas in binary search, you can do it in 4. So hopefully that shows you that you can really cut down on the problem size when you do binary search like this. If you have any questions, feel free to interrupt. This is the pattern that we're going to practice repeatedly over today. All right, let's note some drawbacks. It's not an online algorithm. For online sorting, for getting elements sorted as they stream in, we'll talk about these things called heaps and priority queues later. It's also possible to use balanced binary trees to acquire a similar kind of performance as heaps. But be really careful. I've illustrated the idea of binary search, but it is not at all easy to implement, especially for beginners. So I really recommend that you use libraries. Like, think about the programmers at IBM and AT&T. Like, probably they were around some of the best in the world because they were the only ones in the world doing this. And 90% of them failed to provide a correct solution after several hours of working on it. So just know that what we do today, it's very simple to explain. The tricky part is in the details. The template that I'm going to provide to you kind of helps you short circuit thinking about all the ways that your binary search can go wrong, but there's still a few things that you have to make sure that you get right. That's another quote by the famous Donald Knuth. I don't actually know how to pronounce his last name. All right, so here's the choices that you have to get right. As we saw in the beginning, you have to select your low and high bound first. And I tend to use another variable called best. I might change the slide later and really call this a best candidate, because depending on how you use binary search, you might be returning the value closest, right, to what you're looking for. So that's why I think of another variable called best, just to help me remember that. You'll see different ways that other people write binary search. I'm not going to be presenting those ways because I find those really hard to remember. So the condition that you must do the correct comparison using mid. So sometimes it's the value, right? Sometimes you just pick the nums, you get the index called mid, and you do some kind of comparison with target, right? That comparison is going to be different on different problems, and we'll see different ways in which we'll see this mutate between different problems. Just notice that this slide just says another one. I'll fix that. So if the condition is true, you have to now make a choice. Is it the left boundary that moves, or is it the right boundary that moves? And best usually captures mid, and what I mean by that is that it records values, right? Because you can think of that when you're doing binary search, you want to record the closest thing, so you're going to keep a variable that keeps on tracking what the best candidate is. And there's some times where in a certain window you overshot, so you don't record that value. I'll make this clearer as we go along. It really helps with a concrete example. And in binary search, right, the basic structure of this is while left less than or equal to then right, and there's going to be an if something, and it's going to be low equals mid plus 1, or it might be else mid high equals mid minus 1. Sometimes these are swapped in where they are depending on the problem when you start applying binary search. But we'll see ways in which where we decide how to move the low and the high pointer. So because there's tricky details and because binary search is so useful, you should get comfortable with the bisect library. It's a Python library that just does binary search for you. You can pass in an array, you can pass in a target value for x, you can pass in the initial bounds, and I believe you can also pass in some other stuff, although I haven't really used that. So the documentation's there for you to read if you're interested in what this does. I'll be showing this off of using bisect sometimes during some of these prompts. So first off, let's go through search insert position. And this one is a problem where you simply are given an array of integers, and you want to find the index for target, right? So here, remember, arrays are zero index. This is index 0, 1, 2, and 3. So the output is index 2 because that is the index right here. Also specified in the prom is that we wanted to run it in O of log n time complexity. And you're given this key piece of data. You're given a sorted array of distinct integers. Okay? So it's sorted, and you basically have an array, so you can use binary search. Right? Those are really big clues. Whenever you see a problem that says sorted, you might ask yourself, can I use binary search to help me out here? Here the answer is yes. So what's going to happen is you're going to first establish bounds, right? So what is the low bound? Well, for any array, right, the low bound is going to be 0, right? And for any array, the right bound, what I'm calling high, is actually going to be the length of the nums minus 1, right? That's always going to give you the pointer, well, the index to the right. So if you had an array of, like, let's say 1,000 elements, this index would be 999, and this would be index 0, right? So I've established my high, I've established my low and my high, and now I'm ready to do binary search. I technically will just, the way that I present it to you, I will just keep a best candidate, and this kind of depends on like what I want to do with it, and sometimes I think about it before I actually write down a value for it. When I do binary search, it's always low less than or equal to high, and I always calculate mid in this specific way. This is to prevent integer overflow, but it is essentially the average, right? It's essentially going to be low plus high and doing integer division by 2, right? This is essentially what that is. You can imagine that if you had 2 indices in an array, if these are valid, right, you will always be able to find the mid, because let me motivate this differently. Let's say the index is really high. Let's say it's like 2 to the 31st minus 1, right? And these are two numbers in the that you're using for low and high eventually, because it's going to converge. So if you did low plus high, this would overflow, and basically, because you're dealing with bits, you would start dealing with negative numbers. You would add this and actually get a negative number. This can be really surprising if you're not familiar with integer representations in computers. I'm not going to go over that, but essentially this is to avoid overflow or possibly underflow. What we're doing here is basically, if you think about a number line, and if you can never go above the high, right? So if you added high and low, you'd get a number way over here, right? And you wouldn't be able to represent that without going into a negative number or using different types. But if you go low and you have high minus low, suddenly you just get the value that's as this big, right? And if you chop it in half, you get a distance that's this big. And then we just tack it on into low. So then we end up right here, right? So this is our mid. So that's essentially the same thing, but to prevent overflow and underflow. So with this mid now, we have this value. And the way we access a value from an array, well, you probably know, we just use square brackets and we access it through the index. If value is going to be less than or equal to then target, what should we do? Well, here in this example right here, the value is going to be 3, right? So we're actually going to be comparing 3 with 5, and this is less than or equal to than 5. So where should we move our bounds, right? So low's right here, and high's right here. Well, low better move, right? Because we know that values from 3 and before 3, right, here, don't work, right? So we want to actually move our low to the right side of the problem. We want to consider the values 5 and 6, that range. Now the computer doesn't know that 5 and 6 are there. We just have to move the pointer, right? So low equals mid plus 1 in this case, which means that in the other case, the only other case that exists is values greater than target. We have high equals mid minus 1. And this is what I'm going to mean when I say, so I'm just going to put in a dummy value for best right now. I tend to return this value when I do binary search, but I'm just going to show you right now. A lot of times I will actually print out things. So I'm going to run that, and I'm going to show you the printout. So of course these are all wrong because I didn't update the value that I'm returning. But I'm going to show you the standard output of what happened. So here's the indices. Here's the record of what happened. 0 was our low, and 3 was our high. We chose the mid, which was index 1, right? That value is 3. And then we updated low and high again. Well, it just so happens on next iteration I get to see that I updated low to mid plus 1, and high remains the same. Mid now, when we calculate it, is index 2. Okay? That's actually going to be the answer. And the next loop of what happens is that low increases again, and the value is too high, so we actually go into this part of the loop, and then we finally exit because low is now greater than high, right? So I tend to write it this way. Because I just capture the best candidate that happens each time. And oh, I got it wrong. So you see, binary search is easy to get wrong. Alright, so this happens sometimes when you realize that it only happened, like only this branch happened, right? In which case best never gets updated. So actually, the default value that you might pick is actually, well, because this is a search insert position, and if you have the value 7, right, the value would be all the way to the end of the array. So that should get the problem right for this problem, well, for this test case of 7. But what about for 2? Now I'm genuinely curious, like where did I go wrong here? So 2 should be index 1, that's for sure. Oh, I actually got it wrong for this problem as well. Wow, that's amazing. Well, just to speed this up a bit, I would spend more time debugging, but whoops, that's a really short one. Oh wait, did I do this completely wrong? Oh yeah, I actually switched. This is one thing I'm glad I'm illustrating this. So the value is less than target. The actual comparison is actually different. So what did I do here? So the value I found was greater than or equal to than the target. right, instead of the other way around. All right. Does anyone know why this works better than what I put in previously? Yeah, go ahead. Yeah. So I do that in the previous iteration of the code anyway, but that is kind of hinting at where I'm going with this. So basically when I capture values, right? When I capture values between low and high, when my value is greater than the target, I'm really capturing it from the right. Before I was capturing values by approaching to the value from the left, but if the value is right here, the search insert position says I need to return the target if the index is found. If not, it's the index where it would be. So it is actually going to be, so I actually need to approach from the right, not the left. I'm trying to figure out a way to like kind of explain this better, because it makes sense in my head, but now that I have to explain this in a way that makes sense to other people, yeah, I'm still working on it. But basically, when we capture values, when we do binary search, at least in this format, when value is greater than or equal to target, that actually might be a candidate, right? Because imagine if you had something like 7, 9, 10, and you are looking for 8, right? When the value is greater than or equal to target, right? This 9 right here, this index is the candidate that we want to capture, right? Because 8, this could be the first place where we need to put in 8. That's why we should capture the best candidate on this side. If we did it while flipping this into less than or equal to then target, right? We would actually be saying, hey, 8, maybe we should capture the midpoint here, right? At index 0. But in fact, 8 should fit in here if we were going to add this into the array, right? So that's basically why, it's actually one of the most common mistakes I make when I write binary search, is knowing, is kind of, I flip the inequality sometimes, and I will actually debug what goes wrong based off of the print statements that show up. So possibly less confusing way to write this, if you don't want to use 2 branches, is to actually basically if value double equals target, right, then you would just return mid and maybe not worry about this so much. I tend to not write this, and in fact, I can't actually guarantee that this strategy is going to work in all cases for this problem. Just because of the way that I write binary search now, I kind of don't think about it as much anymore. I just follow an existing template. So feel free to ask me questions. I'm sorry that wasn't like the smoothest explanation. I'm going to show you one other thing that you can do for this problem. And it is basically this. So let me just pop this in. Yeah, pop this in. So basically you can use the bisect library, right? If you didn't actually write out the code, this is such a well-formed thing that you can just use the library bisect. You use bisect left, you pass in the array, pass in the target, and basically that encapsulates all the logic that we've tried to do. So that's search insert position. Any questions? Yeah, that was just on the screen, but what you can do is just bisect and then do bisect left. And that's all it is. Yeah, that's just one line, right? It's encapsulated into a library, so that's all you do. It is way easier, but as we'll see, binary search is used in more situations than just an array. You'll see a lot more of that in part 2 of this lecture, but also you'll be seeing more of it today as well. Yep, it's a required argument. A here is an array, and you have to be looking for a specific x. There might be a way to pass in some kind of comparator here. Yeah, but you can read the docs. Get familiar with the bisect library if you're going to do binary search. Great question. I actually have, that's actually part of my next example. So I'm going to show you how to do the square root of x. And if you look at this problem, oh, whoops, whatever, you can ignore the code, I guess. Think about this problem. There's actually no array here, right? I'll give you a minute to read over the problem, but I'll also read it to you. Also, if you want to follow along, just remember that the slides are uploaded on Google Drive. So just look at the announcements channel for that link. It was probably posted 2 weeks ago. So it has all the slides, and you can click on the links if you're having trouble navigating. So I'm going to read the problem now. This is square root of x, so you're given a non-negative integer x. And you want to return the square root of x rounded down to the nearest integer. And the returned integer should also be non-negative. And that's actually due to constraints. They didn't even have to say that, because if you look at the constraints, the value that they're going to give you is 0 to 2 to the 31st minus 1. This value is special because this is the biggest positive value that you can represent as an integer. All right. So it also specifies in the problem, you must not use any built-in exponent function or operator, right? So in Python, I believe you can write something like pow, take x to the 0.5 power. Well, I guess this is Python, this is C++ or something. So basically, how do we find the square root of x? So I'm going to give you a moment just to think about it. Dang, it's already 12. I'm slow. But take a minute, and I'm going to talk to you about a few ways to think through this problem and how binary search might fit. Yep, but for this problem, you know that the biggest input is going to be 2 to the 31st minus 1. So yeah, this is going to be the biggest thing that's possible, right? We might have to, we can set this as our bound, upper bound. Just know that, like, because x is actually going to be this value at most, we know that the square root is actually going to be significantly less than that, right? We could actually say that the upper bound is 2 to the 31st minus 1, and do, like, I don't know, divide by 2 or something, right? That'd also be a proper upper bound, right? But if you're lazy, you can just use 2 to the 31st minus 1. It's going to work out either way, even if you choose a bound that's really huge, much bigger than the problem. And binary search is going to have no problem cutting down that problem to size, because remember, it is a log n algorithm, right? So 2 to the 31st is going to be around, what, 10 to the 9th? I'm going to bring out my console. Python 2 to the 31st, right? I'm going to do minus 1. All right, so it's that number. So it is around 10 to the 9th. Yeah, so this is like 2 billion and something. But remember, when you do a log, do I have log included? Math.log from math import log. Okay, maybe that works. 2 to the 31st minus 1, and do it base 2, right? That's going to be 31 comparisons, right? So it's really not going to be a problem for binary search, even if we overestimate the high bound. As long as we have our logic correct, we can get this done in 31 comparisons, worst case. Yeah. Yeah, how you phrased it itself is a search, right? We are looking for a value, right? So we can kind of think of this number line, right? And x is right here. And we're really looking for the floor of square root of x, right? Because it's rounded down to the nearest integer. So to find this value, we basically have a bunch of candidates, right? So we're saying, well, what if we just look at all of these as candidates, right? Like, that's a possible way to look at it. And, you know, a very naive way is just to look at, well, what about 0 squared? What about 1 squared? What about 2 squared, right? Can it get us to x is the question. And once we overshoot, we know that the one before that is the answer, right? So x is 8. Well, if x is 8, right, we could try 0 squared, we could try 1 squared, and still less than, right? We try 2 squared, it's still less than. We try 3 squared, and oh, that's actually 9, and we overshot. So actually, we know that if we were to find the square root rounded down, it had to be the one previous, right? So this is how you can kind of think of this as a search problem. And what I've illustrated here is a linear search, right? It is actually slightly better than a linear search because we actually square the number in order to find x, right? So in terms of n, this is actually, it's a linear search strategy, but because of the operations that we're going to use, it's actually going to be O of square root of x, actually. That's actually their time complexity. It's actually possible, well, to do better than that. If you think about the graph of square root of x, right? What it moves like this, like a parabola. Whereas when you look at log, it actually moves a lot slower, right? If you graphed out these two functions of square root of x, or I guess 0 is right here and stuff. They probably cross at some point. They cross at like 1, right? Don't they? Or something. Dang. It's been a while since I've like done graphing. Anyway, the point is that log n is actually going to be faster than the square root of n. So this works, right? You can use this strategy and you can always guarantee correctness. What we're going to attempt to do is phrase this a little bit differently into binary search problem. And here's what you notice, right? All the numbers are totally ordered, right? Numbers on a number line, right? They're in sorted order naturally already, right? And we know we have a high bound and a low bound, right? So this naturally like shows us that like, hey, we're doing a search. The elements are actually ordered. We're looking for something called the floor of the square root of x. Can we use binary search in order to do that? Well, the answer is yes, of course. Otherwise, I wouldn't have shown this example. So, what are bounds first? Well, the bounds we can just establish as low and high. We don't expect high to be the actual value, except of course in cases of 0 and 1, right? Or I guess, yeah. All right, so those are our established low and high bounds. And I'm gonna start like writing the while loop. Well, it's already pre-baked. But you can see that basically I always have low less than or equal to high, and I make my guess, right? This is actually the mid, right? This is the mid between low and the high. It's actually going to be right here, right? Maybe overshot or something, but that's okay, right? And what I do now with this guess is I square it, right? So I do guess and I square it, and I say, hey, is this going to be less than or equal to than x, right? Of what I'm trying to find. If I square this number, can I get to where I start off with, x? And if the answer is no, then I know that my high should actually be moved to right here, right? Because I know all the values from here are just going to overshoot x, right? So I cannot do this. Sorry, that looks like an x, but like the value we're finding is also x. So cannot use these, right? So this is essentially how you narrow down the binary search. Again, it's the same thing, right? We have a low bound and a high bound. Every time we cut in the middle, we have our guess, right? This is our candidate. This is an index, and we look up that index, we find the value, we square it, right? That's what's going on here. Except there's no value lookup, right? Because the guess itself is the value we're using. So here's what happens, is that when we square it, if it's less than or equal to than x, and remember, we're approaching from the left because we want it rounded down to the nearest integer. So best always captures the element like that is going to be less than or equal to x, right? Because once we exceed, once guess is like greater than x, we don't want to capture that as the best candidate that we've seen, right? So this is basically a standard binary search. You have to decide, like, hey, based off of this comparison, right? Get the comparison correct, and then decide, like, okay, if that's the if block, do I move the low or the high? And the else block is the opposite, right? If I move the low in the if block up here, I need to move the high in the else block. And if it was a different way, if I moved the high in the if block, I'd move the low in the else block. And yeah, let me know if there's anything confusing. guess, here, let me print that out. So guess should be the square root of x. It's our candidate for the square root of x, rounded down to the nearest integer. Is our best guess for the square root of x. Right? Because we're guessing each time, right? If I find a number here and I was like, oh, it's actually greater than what the square root of x is, then I know that this guess is wrong, but I get to eliminate all the values that are here, right? And I get to just focus on this section of the problem, right? Each time I'm guessing is from a calculation of low and the high, right? Unlike doing an array problem, what's different about here is that the low and the high are actual values. Right? In an array, we might have to look up low and high. I mean, we'd have to look up the mid, right, in the array. But here, we don't need to do a lookup in any array. In fact, there's no array, right? We're just given a value x. So let me print this out for you. Hopefully that might make more sense. So if x is 4, right, low starts at 0, high starts at 4, we make the guess 2, right? And 2 times 2, right, it's our guess, is less than or equal to than 4. So because, we're right under that or equal to it, we know that that's our best candidate rounded down to the nearest integer so far, right? We want to try higher values now, right? Because we don't know that this was definitively the answer. If you wanted to, you could have a third branch. If guess times guess double equals x, then you just return. But here I just encapsulate it into just one if branch. So that's what happens here. That's why this loop goes another time. Low is now guess plus 1. So we increment that in low, and then we make our next guess 3. 3 squared overshoots 4, right? 3 squared is 9. It's greater than 4. So we don't want to capture that as a possible answer. Let me show you this with like 1 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see the printout that it's going to do some comparisons, right? But it dramatically lowers each time. So this is going to be, what, 500 million, right? So it's 5 times 10 to the 6. If you square that, and remember, we're doing this in Python, so it's not going to overflow if we do this, but if you were in like C++ or whatever, you should watch out if you're going to actually be doing like a square. So that's too big, right? But we get to chop down half of the search space. So high is now less than 500 million. And we take the midpoint, right? And we're going to take the midpoint for a while. It's only going to be high that's moving, because we're going to be overshooting the square root of 1 billion a lot. It's only until we chop things down until high is 61,000, right, that we make the guess, and we finally say that, hey, this actually undershot, right? This is actually less than a billion if we square this number. So now we get to move low up, because we know that, hey, all the values to the left, right, this is the best candidate out of all those values from 30,516. Now let's look at the right half finally. And the right half isn't up to x, right? The right half goes until what high is. So you can kind of see this, like, it'll take turns between moving low and high, right? When high moves down here, finally to 32,422, then we move our low again. So we keep doing that a few times until we finally capture, right? We capture the value coming in from the left until we finally have the value. Does that make more sense or still confusing? Yeah, let's do that right now. Well, not exactly 1 billion. So this is going to be but the closest integer rounded down, right? So it shows us that value, right? So I just squared it right there. And let's try 31623, right? Because if this, yeah, it goes over, right? And if you see, we actually tried it 31623. And because it went over, right, we did not go into lines 10 and 11, right? We did not capture that as our best guess for what that square root of x was. We only captured it when we were underneath or equal to then this value. Correct. Right. And it's easy to see that in this problem, that this is a comparison that works. I picked this problem because it felt most natural to show you why, like, I tend to do things in like 2 branches. But honestly, sometimes it's like out of habit. There might be a better way to present this material, but I'm not going to be able to rework it like on the fly right now. It's also 1221. Sadly, again, I thought I'd be like farther along, but hopefully some of this repetition is helping this sink in for you. I only have 2 other problems, and I want to show you this problem because it shows you an invariant where you do not need the numbers to be sorted to use a binary search. What you need to guarantee is an invariant. 300 is longest increasing subsequence. It's probably it's probably my favorite LeetCode problem. So those are the 2 problems that I was going to talk to you about. Okay, so let's take a break, but one thing I want to do before we take a break is that I, for some reason, somehow messed up and actually didn't show you one of the key slides I was going to show you before doing the problems, which might have made it a lot smoother. Okay, so I'm going to tell you the reasoning behind this template. So there's many ways to write binary search. Some people don't use less than or equal to then. They just straight up use low less than high. And they make the condition different in that it just might be a value less, like they do the conditions differently so that it's not symmetric. So they might move low to mid, but high to mid -1. I find that really hard to remember and to reason about. So I keep this template in mind because it's the one that I found to just have the least amount of thinking for me. So if you notice, it's symmetric. Low moves to mid +1, high moves to mid -1. No exceptions, no variation. Low is always less than or equal to then high. And there's also no exception to this rule every time I write binary search. When I write binary search, low has to be the lowest possible value that can be an answer, right? I never start from like -1 if -1 cannot be an answer. High is the highest possible value, and so for an array, it's the last possible index, right? If I'm looking at an array. If I'm looking at a possible search space for an optimization problem, which we're not going to talk about today, this has to be a valid answer. When you set up binary search this way, it is always guaranteed to converge, meaning that you will never get a time limit exceeded error because your binary search runs in an infinite loop. If you set it up this way, I guarantee you, where you made a mistake was in setting up the bounds for low and high. This guarantees convergence, where you set it up this way. You will never have a time limit exceeded or an infinite loop if you do it this way. you will always advance low or high by at least 1 when the problem size gets very small. That is why I recommend this setup. The reasoning for this mid being calculated this way is for integer overflow, but you will still have to keep in mind that when you deal with optimization problems that go past like 10 to the 9th, you're going to have to use longs anyway. But this helps you prevent some overflow errors, especially when you deal with an array. So keep that in mind. That's why this is there. This best is typically a value including somewhere between low and high. It might be offset to be outside this range, but this is one part that takes thinking about what the best candidate should be whenever you do binary search. The condition you're also going to have to think about each time of what you're comparing, right? I tend to find that if I have to guard for the case where this block is never triggered, I have to initialize best and I have to think about why it's going to be that value. But basically, I capture the mid in almost all cases. And so if you can see here that in the code, low is paired with best, right? This means that best, I'm actually approaching the answer from the left-hand side. This is important for problems like square root of x, right? Because I'm approaching from the left-hand side in order to find the best answer that I can. You might see it the other way in some problems, right? You might actually see high equals mid minus 1 at this line, whereas low then has to be in the else block. In this case, best is capturing the best guess coming from the right-hand side of the problem. So those are the things to keep in mind when you use this template for binary search. So I wish I had shown you that before, or just shown you right after search insert position, but I just wanted to show you that. This is the template I use. I basically can copy and paste this into like almost any binary search problem and just do the 4 things that I mentioned. The 4 things to get right. Set the low and high bound, what condition I'm using, where to use the low and the high, and where to capture the best guess when I do use the binary search. So that's why that template exists, and that's why I use it. Sorry this took so long. Let's take like a 10-minute break now, but feel free if you want to ask me questions. You can ask me now, or you can ask me after the break. All right, so there are some times where your problem space, like your low and your high bounds, might actually exceed the bounds of an integer, right? So an integer max is going to be like 2 to the 31st minus 1, right? It's going to be this value, right? But it's possible that like integers might not be appropriate for your problem. If you're high bound, or if you're high bound, the answer might all the way be up to like 10 to the 14th, right? 10 to the 14th, well, that's going to be greater than this value, right? Than max integer. So I'm just saying that you're going to have to think about like certain times where you might have to use not an integer type, you might have to use a long type, right? That's going to give you more bits. And depending on the problem, like let's say you have a 64-bit right long, that's going to allow you to go up to like what, 2 to the 64 minus 1 or something like that. Wait, no, 2 to 63 or something. But yeah, so basically care about your capacity for your integers. That's all I'm saying. All right. Well, feel free to keep asking me questions or just take a break. Let's come back in 10. I might only go through like find peak element and then we can do some slides, but then I have some group work for us to do. Cool. See you in 10.